Hey physicists, today we're going to talk about a topic that typically students struggle with, and that is electric potential or voltage. And one of the ways that we're going to start is to try and build a foundation that'll help you understand that a little better, and that's by tying it back to gravity. So if you remember when we talk about fields, the one field that we've studied already has been the gravitational field. And that is, if I have the Earth here, the Earth is trying to pull everything towards it. So you have this gravitational field that's pulling down. And so if I pull this baseball and I lift it up or against or away from the way that it wants to go, then I've given that baseball potential energy so that as soon as I let go of the ball is going to fall back towards the Earth. So I would need to do work to push the object up against gravity, and then that would give it potential energy. Now remember, the equation that we use for that is mass times gravity times height, or another form of force, which is the weight, times the distance, which is the height. So mgh is our gravitational potential energy. Now, if I analogize that to electric potential energy, I have this plus charge here and have a minus charge. What way does the minus charge want to go? Well, it wants to be attracted towards the positive charge. So what way would I do work on it? I would lift the negative charge up or away from the way that it wants to go. And that would give it a form of electric potential energy, okay? So work is needed to push a charge against a field and give it electric potential energy. Now remember, when we talk about gravity, there is only one form of mass, but when we talk about charges, we have two different kinds of charges, the positive and negative. So I might move the negative charge away from the plus charge in order to give it potential energy. But imagine if this negative charge were a plus charge, it wants to go away. So if I'm going to do work, I'm going to push it towards the positive charge because that would be the way that it doesn't want to go. And notice that the electric potential energy equation mirrors this gravitational potential energy equation. We have a fundamental unit, which is mass there. We have a fundamental unit, which is charge here. We have a gravitational field, G, and we have an electric field, E. And in both cases, then we have a distance that the object is moved away in that field in order to give it that potential energy. So if I take and I divide both sides of that electric potential energy equation, so picture back here, I have this QED is equal to the potential energy. If I divide both sides by Q, then we're going to take and define this side of the equation as another physical quantity, and that's what we're going to call electric potential, otherwise known as voltage. Okay, so voltage is defined to be energy per charge. Voltage is energy per charge. Voltage is not energy. It's how much energy there is per charge. Okay, so it's potential difference is one word that we talk. Voltage is a scalar value. And then what does voltage measure? It actually measures either how much energy that charge will gain or lose, or how much work that a charge can do. So it's talking specifically, it does have the energy there, but I'm looking at how much energy per charge, how much energy there is per charge, or how much work each charge can do. So are you starting to sense the importance of this? It's not energy, but energy is a part of it. Okay, so if the field is constant, then we can use this V equals ED, which is the right side of that equation. If the field is not constant, then we have to talk about plugging this in. And then you plug the equation in for E, and if you remember in the last chapter, we had KQ over R squared, and when we do that, these two distances cancel out, and we're left with that the voltage is KQ over R. So that's in a non-constant field, or dealing with a point charge. This is in a constant field. So the next thing we probably need to talk about is the elephant in the room. You may have noticed that on this particular slide, I used several different words to describe voltage. We talked about it as being an electric potential here. We said it was a voltage here, and we also said potential difference here. And that's one of the things that makes this a little confusing for students, that there are several different words for voltage that we're going to talk through, and you should probably jot these on the front of your notes or your front of your foldable and just sort of keep them in the back of your mind. For what we're doing as a real basic level of physics, all of these words, potential, potential difference, electric potential difference, voltage, and electromotive force, EMF, they all mean the same thing. They're all other words for voltage for what we're doing. Now, if you were to become an electrical engineer, absolutely, there are certainly small differences in each of those. And probably the best example for me to give for you would be if we go back to that potential energy idea. So let's say that I have a potential energy. I have an object, this is maybe the Earth, and I have that baseball again, that I'm going to lift the baseball up against away from the Earth. What would I say my initial potential energy is when the ball here is resting against the Earth? Wouldn't I say that that initial potential energy is 0? And then, I don't know, maybe I give it 100 joules of energy, so I've lifted this up to where it has 100 joules. Now, can't I say that the the gravitational potential difference is 100 joules? The difference between 1 and 0 is 100. And so in essence, that potential difference is the same as whatever the potential is. And that's kind of how we'll do a lot of it. Now, if you think through maybe this potential energy, it was not 0 to begin with. Maybe it was already off of the ground and it had a potential energy of 10. So the potential difference there is going to be 90 joules. That's what we're going to say. Let's save that for upper level electrical engineering. And for now, we're just going to assume that our potential is the same as our difference based on all of those. Okay, so that kind of gives you an idea. Those 6 words, all for what we're doing in this class, all mean the same thing. They all mean voltage. So if it's asking you to find the potential, you're looking for voltage. If it's asking you to find the electric potential, you're looking for voltage. If you're looking for the electric potential difference, you're solving for voltage. Okay. So moving on, in a uniform electric field, so notice that we have this point charge here. Notice that as this goes away, that the field lines are going to get spread out further and further and further, right? As opposed to if I take 2 parallel lines, notice that I'm going to have these parallel lines of field where the electric field is constant in there. And this was developed by Alessandro Volta. He was about the same time as Coulomb, which was shortly after Sir Isaac Newton. And he's the one that took these parallel plates and said, well, these point charges are very interesting, but in order for me to really study electric fields, I need to have an area where the field is constant. And that's where he developed this idea that if I take 2 plates, so maybe this plate is going to be hooked to an electrode that is a plus electrode, so I get positives up here. This plate is hooked down here to a negative electrode, so I get negatives down here. And that's where I would end up with an electric field. Remember, it goes out of positive into negative. So I would draw the field as coming down, and they would draw evenly spaced, assuming that we're talking inside the plates here and not on these goofy curved parts of the edges. Okay. So inside there, we have a uniform electric field, which my face is covering up. Okay, so uniform electric field. So nextly then, the potential energy difference. So if I look at this, so here's my plus charge plate, here's my minus charge plate, and my electric field, remember, goes out of positive into negative. So I'm going to draw those arrows down. Now, at the top here, why does that negative charge have a low potential energy? Yes, because isn't that where the negative charge wants to be? It's attracted to the positive, so the closer it is to the positive, the happier it is, the more it wants to be there. So if I move it down away from where it wants to go, I push it towards that negative plate away from the positive plate, then I'm going to be giving it a high potential energy. Now, let's say I take a -2 charge and I push it towards the other end, the exact same thing happens. It wants to be towards the plus plate, so it's going to have a low energy at the plus plate, but it's going to have a high energy at the minus plate. Now, the next question then is, why would that -2 charge have more potential energy than the -1 charge? Well, doesn't it make sense that since there's twice the charge, there would be twice the energy? You can even think back through to that U equals QED. If I have 2 times the charge here, aren't I going to have twice the amount of energy, right? Okay, so electric potential energy, potential difference. Here we go. I have a +2 charge. Does this have a high or a low potential energy? And the answer is it does not want to be next to the positive plate, which means it has a high potential energy. So as soon as we let go of that +2 charge, what's it going to do? It's going to float down to the negative plate, in which case it will have a low potential energy, right? Now, same thing, a change in potential energy. Isn't a change in potential energy equal to work? So anytime we talk about that, we can talk about, well, who did the work and how much work was done? So if I push it towards the plus plate and it goes the way it doesn't want to go, who did the work? Me or the plates? It had to be me because I'm pushing it the way it doesn't want to go. Now, as soon as I let go of that charge, isn't that charge going to be going towards the bottom, towards the negative plate? And why is it doing that? Because the field between the plates, so in that case, the plates are doing the work. Okay, moving on. Here we go. So I have a -2 and a -1. Which of these has a greater electric potential energy per charge? Okay, not greater electric potential energy. We already know that the -2 one does, but which one has a greater potential energy per charge? So remember earlier we said, what is potential energy per charge? Isn't potential energy per charge voltage? So which one of these has a greater voltage? And you can think through, that one has more potential energy, but they are both going to have the same electric potential. Well, why is that? So when we go back to that equation and we said the potential energy is QED, remember voltage is defined to be U over Q, which is ED. And if I have twice the charge with twice the energy, then isn't that ratio going to cancel out and I'm going to be left with the exact same value of the voltage no matter how much more charge I get, which is one of the things that's beautiful about voltage, because it doesn't matter how much charge you have, you're going to have the exact same amount of voltage. You will just have a different amount of energy. Okay, so potential energy and potential energy difference. So here we go, one more. So I have a -2 and a -1. Which one has more potential energy? It's going to be the -2 one. Now, where did it have the potential energy at? Did it have it up on the plus plate or down on the minus plate? Which one gives it more potential energy? Since these are negative charges, then the answer has to be whenever it's down on the minus plate, it has more energy. Now, the question was, we just watched those go from the top plate to the bottom plate. Who did the work? Me or the plates? So it moved the way it didn't want to go, which means that I had to do the work and not the plates, right? So which of these has experienced a greater change in electric potential energy? We just said it was the -2 one because there's more charge there. Which of these has experienced a greater change in electric potential energy per charge, which is voltage? And remember that they're going to have the same amount of voltages because it's a ratio that cancels out. Now, here's a really, really, really super basic analogy to give you an idea of where we're going with this. This is a car battery. I might say that the plus end of the terminal has 0 voltage. The minus end of the terminal has 12 volts. So a car battery is 12 volts. Think through the circuit that each electron, the battery is going to give each electron 12 joules of potential energy. Now, again, this isn't exactly true. This is just sort of an analogy or a metaphor so that you can see where we're going with this. So it gives it this energy. I lifted it up so you can picture this as kind of like gravitational potential energy. And as the electron then flows through the circuit of the car, it loses that energy because it's giving the energy to something else. So maybe the electron goes through here, the dashboard lights. And then maybe it is going through, at this point here, it goes through the stereo. Again, this is a really, really loose metaphor. And then at this point, it goes through the turn signal because you're sitting at a stoplight ready to go. And then at this point here, maybe it's going through your headlights. Okay, your headlights are on the front there. And then what it would do, by the time it gets done with all of that circuiting, it ends up where it's given all of its energy away into the other parts of the circuit in your car, and it returns back to the battery with no energy so that the battery can recharge it again to give it energy to go back and complete that cycle. Now, again, this is a really loose metaphor, but in essence, it gives you an idea of what's going on with that voltage. It's the amount of energy per charge, so the battery is giving each charge a certain amount of energy, and then that charge is giving the energy away to the different parts of the circuit so that it can run based off of that energy. So, sample problem. The electric field is 625 newtons per coulomb between two large charged parallel plates that are 4 centimeters apart. What is the electric potential difference between the plates? And what work would you do to move the proton from the negative plate to the positive plate? So the first thing I've done is I drew a picture here. I have a positive plate and a negative plate. I know that they are 4 centimeters apart, or I'd have to convert that into 0.04. And then we have this proton. that is here, and we are going to move it up towards the positive plate. So if we're talking parallel plates, remember that we have a constant electric field. And if we go all the way back to the beginning, remember that we said the electric field is either going to be VED or it's going to be KQ over R, right? KQ over R. And which one of those dealt with a constant electric field? It was the VED, and given that that's what we're given, so that would make sense. So the next thing I can do is plug into VED, the 625, the 0.04, and that gives me that there is a voltage of 25 volts in there. Now, what work would I do to move the proton? Remember that that is going to be the work is the electric potential energy, which will be charge times voltage, or another way you could say this is it's charge times E times D, but we already did E times D, 25, so we can plug in the 25 for the voltage, and since it's a proton, we're going to put in the 1.6 times 10 to the negative 19th, and there would be a certain amount of potential energy there that is 4 times 10 to the negative 18th joules. Now, notice that that's a really, really, really small amount of energy. And it's not that we don't use that energy, but the way that we use it is we can use a lot of charges with a really small amount of energy, and that gives us a lot of energy because of how much charge that we're actually dealing with. So lastly, I'm just going to run through this real quickly, but it sort of gives you an idea of definitions, derivations, how did we get things, what are the units for each of them, what are the equations. It wouldn't hurt for you to screenshot this. So this is electric force. Its symbol is an F in an equation. It's a push or pull on a charge. It is defined to be the energy per distance, or the field times a charge. We measure force in newtons. And then the equations we could do would be KQQ over R squared if it's a non-constant field, or EQ if it's a constant field. Same thing, electric potential energy. It's the total potential energy. It's a force times a distance, or the field times the charge. The joule, it's measured in joules then, and then we would have KQQ over R, which is going to be, if it's a non-constant field, or that negative QED or QV if it is a constant field. So that gives you an idea, just looking down over those, what those are. If I go to this one, I found this one from another AP physics teacher. I don't have, I thought I had it on one of the pictures, but I don't have it to give him credit. So I'm sorry, whoever you are. This is totally not mine. I got this from someone else. So it takes those four concepts, the electric force, the electric field, electric potential energy, and electric potential, and shows how this part in the middle is dealing with charge. So if I go to the right, I'm dividing by a charge per unit charge. So I'm going to divide this by a charge to get rid of it. If I go to the left, I'm multiplying by a charge or adding the charge in. If I come up or down, then I'm really dealing with a distance. So when I come down, I'm multiplying by a distance, and that gets rid of one of the distances. Or if I go up, I'm dividing by distance, and that gives me a distance. And it shows you the interplay between each of those different physical aspects dealing with electricity or electrostatics in that flow chart. Each of the top equations then are the equations for non-constant fields, and each of the bottom equations are the equations for constant fields, and then the units for each of those are at the bottom. This would be another one that if this one didn't make sense to you, then maybe you are doing this one as an idea. You're screenshotting that and picturing that and getting an idea of that. So again, when we talk about the electric potential, the major idea is that electric potential is the energy per charge. So you're going to take the amount of potential energy there is, divide it by the charge that you have, and that will give you the voltage or the energy per charge. We have several different ways that we can talk about voltage. It's going to be electric potential, potential difference, electric potential difference, voltage, EMF. All of those are different ways that we can describe what a voltage is, but we want to, for what we're doing, we're going to say they're all the same, even though there are slightly nuanced differences between each of those. So I hope that helps, and that is a summary of what electric potential or voltage is.